it is for me a pleasure and the honor to be part of this conference. Today I will tell you something about some recent work and some work in progress with Lorenz Eberhard. And I will try to explain you how one can compute string theory correlators on three-dimensional anti-de Sitter space. So we are interested in string theory on ADS space in view of holography. So this theory is believed to be dual to some conformal field theory living on the boundary of ADS. And what the probably simplest setup is dS3 with pure and SNS plots. Because in this case, we can study string theory via some conformal field theory living on the worldsheet of the string. So similarly to the flat space case, we have a CFT on the worldsheet. And this is the so-called SL2R Vezzomino-Witten model. Actually, this model that gives us access to string theory is believed to be completely solvable. On the other hand, this doesn't mean that it has been already solved. So what I will present will be a step towards a full solution of the model. Now, what is the novelty for ADS3 and why should you be interested? So on the slide, you can see a cartoon. Usually we think of ADS as a cylinder. Now, we will study correlators in Euclidean signature. So in this cartoon, we think of ADS not as a cylinder, but we map to a sphere. So the surface of this gray ball is where the dual CFT lives. And the bulk of this ball is ADS3 space. And you can see that inside the ball, there is this blue-green surface. This is the worldsheet of the closed string. And you can see there are various sheets. You can count 1, 2, and 3 here. And you have 4 insertion points. So you have 4 points where the string is attached to the boundary. So this is the cartoon of a 4-point function. Now, what is new for ADS3 is that you can see that close to the insertion point, so close to where the string is attached at the boundary of the sphere, you see that the worldsheet can wind multiple times. And in the cartoon on the slide, it winds twice around each insertion point. But many other configurations are possible. And this is the main novelty, but it's also the main difficulty, since not many results for these correlators with winding are known, and not even the 3-point functions where all 3 vertex operators have winding is actually known in closed form in the literature. And this is exactly the gap that we want to fill. Now, let me describe our setup. So we study genus 0 bosonic string theory. This is not really a limit if you are interested in supersymmetric string theory, since you can decorate with free fermions, and the bosonic correlators are the basic ingredient also to compute superstring theory correlators. Now, everything I will say in this talk is just a consequence of the symmetries of the model, nothing else. And in particular, what is important is the symmetry algebra of the CFT living on the worldsheet. So I told you is a CFT, so the symmetry algebra is SL2R level K. So here on the screen, you have some commutation relations of the currents. It's not important that you memorize them. The details are not relevant, but I wanted to include them since everything I will say is essentially just a consequence of these commutation relations. So in analogy with flat space string theory, you can think that these are the analog of the A-Dagger and AM commutation relations that you have in flat space. Now, we compute correlation functions of what? Let me describe how the vertex operators look like. So I will start from the better known correlators with no winding, so 0 winding. So you see this V carries a big 0 on top. This tells you is the vertex operator with 0 winding. And then if you remember the cartoon I presented before, there is an insertion point on the boundary where the string is attached. So this is labeled by the x, which is the boundary coordinate. Then we also have the coordinate on the surface of the green worldsheet, and this is the z worldsheet coordinate. So this is the coordinate you want to integrate over to get the actual string theory correlator. And on top of these, of course, we have different representations, and these different representations are labeled by some spin of SL2R, since this is our symmetry algebra. And you can study how the currents behave close to these vertex operators, and you find some short distance behavior. And you can see here that this is quite simple, since you have just first order poles, and then everything is regular. And if you stare at the second line, the first order pole of the J3 current reads the conformal dimension of the space-time theory. So it's the conformal dimension of the CFT living on the boundary of the dual CFT. And in this case, it happens that it's just given and coincides with the spin J in SL2R. Now, these are the well-studied correlators in the literature, but what does it change when we go to non-trivial spectral flow? So first of all, you see on top of this V, there is no longer a 0, but there is a W. So this labels the integer that tells you how many times the string is winding close to the insertion point. So it's a non-negative integer. And then we have again the X labeling where the string is attached to the boundary, the worldsheet coordinate, which is Z. But now it's no longer true that the spin and the space-time conformal weight coincide. So now there are two independent parameters, and this makes manifest one difficulty in computing these correlators. When you have winding, you also have one additional quantum number. So H pops out where before it was not in the game. And if you study OPEs, similar to the one I presented in the previous slide, now there are much more involved, since they include higher order poles. Now, as I told you already, our strategy is just to impose all the symmetries that the model is known to obey. And unfortunately, these symmetries are not known in closed form, but they can be worked out case by case for any choice of winding. So what we do is to explicitly write them and solve them for zillions of examples. We have more than 200 combinations of different spectral flows. And from these many data points, we are able to guess a formula that interpolates and propose a closed solution for 3.3 and 4-point functions. Now, what emerges from this analysis is that knowledge of the unflowed correlator, so the one that has been deeply studied in the literature, the one where no insertion point carries any winding, will lead to a complete knowledge about the flowed correlator. So once you know the properties of the correlator with no winding, we will be able to deduce all the properties of the correlator with winding, the quantity that have been missing since years. Now, let me go through the various symmetries that the model has and how we approach them. So we start from global symmetries. So we have, for example, translation symmetry, rotations, dilatations, and so on. And these allow you to fix the position of 3 of the insertion points. So say that we fix them at 0, 1, and infinity. And if we deal with 3-point functions, the xi and zi dependence is fully fixed. If instead we deal with 4-point function, we have, of course, some residual dependence on the fourth field, on the fourth insertion point, x4 and z4, or if you prefer, on the cross ratios. But our symmetry algebra is not just global symmetries, it's much more. We have the whole affine tower. So we have all the modes of these Jn currents. We have all the Jn's, not only the J0s that correspond to global symmetries. And in fact, affine symmetry gives rise to additional constraints. These have been worked out a couple of years ago, and indeed they give new constraints for the correlators we want to compute that have winding. But what is unfortunate is that these constraints are very involved. So here is just an example. It's not important all the details, but here is just an example of what these constraints look like when, for example, all correlators have winding equal to 1. So you can see there are some derivatives in the xi's. So these are differential equations in the xi's. But at the same time, you have shifted values of the hi's. So you see on the first line, you have h1 minus 1. But on the second line, you have h1. And on the third line, a different h is shifted up. So these are at the same time differential equations and recursion relations in the h's. And this was essentially the bottleneck. So it's difficult to solve these constraints. Now, the approach that we adopted is to use a Fourier-like transform. So if you trade the variable h for some auxiliary variable y, or I should call conjugate variable y, the recursion relation in h are turned into linear PDEs in y. And then you have a system of these linear PDEs, and you can try to solve them in Mathematica case by case. And this is what we have done for many, many cases. And given the complication of all these constraints, you would think that the solution will just be horrible. But what we were surprised by is that in the end, the solution is quite simple. And we don't know by first principle why we should get such a simple answer. So let me introduce this solution by an analogy. So if you look at global symmetries for the correlator with no winding, the unflowed correlator, you can fix the dependence of the x's completely up to an unknown function of the cross ratio. So you see here on the first line, you have x12 is x1 minus x2. And f is an unknown function of the cross ratios. Now, the solution of the affine symmetry instead of global symmetries for correlators with winding instead of no winding looks very similar. You just have to trade the xij differences for what we call generalized differences. And then the formula will just be the same. And again, we have a dependence on these generalized differences and an unknown function f of what one could call generalized cross ratio. Now, what are these generalized differences? So they are linear combinations of the yi's in yi coefficients, the conjugate variables that we introduced in our Fourier-like transform. And they are linear combinations of some polynomials. Now, these polynomials have a precise mathematical description that I don't want to dig into, but what I can tell is that these polynomials encode the geometry of the problem, and they are related to the existence of a covering map of the boundary sphere. So these have a precise definition and can be worked out case by case. But what we still don't know is what this unknown function f is. This is the last piece of ignorance we have for a closed form of these correlators. And the question is, can we constrain this further? Yes, because we have still one bullet to shoot, and this is the so-called Knislitz homological equation. So in particular, this follows from the fact that you can write the translation operator, what you usually call d by dz, on the worldsheet in terms of the J currents, the currents of the SL2R algebra. But you know the action of these currents on the vertex operator. So the left-hand side will give a derivative in Z, the right-hand side will give second derivatives in X. So you obtain a partial differential equation, and you can try to solve this differential equation. Now, if you apply this differential equation to the solution we found above, this will reduce to a differential equation for f. Were we able to solve this differential equation, we would have won. But unfortunately, we don't know how to solve this differential equation. And what do you do when you are not able to solve a differential equation? You search in the literature if someone else met before you the same problem. And indeed, this differential equation is well known. Is the differential equation a correlator with no winding would obey? So if you apply the Casey equation to a flowed correlator, to a correlator with winding, this implies for the unknown function f, a differential equation that a correlator with no winding will obey.
You have five minutes.
Thank you. So we believe that this is a strong suggestion to say that f, the unknown function f, is the unflowed correlator itself. In the end, they solve the same partial differential equation. And all this is consistent with all other constraints. And this is a non-trivial check. And now I'm ready, and you probably know all the ingredients of the full proposal that we give for 3- and 4-point functions of these correlators with winding. And I know this is a 3 lines formula, is something that you should not put in a slide, we are told. But I have put it here because by now you know all the ingredients of this formula. So let me start from the left-hand side. The left-hand side is the correlator we want to compute. So we have 4 vertex operators with winding Wi. And if we go to the right-hand side, let's start from the second line. These are the generalized differences that I introduced before. And on the last line, before we had this unknown function f, we are arguing that this unknown function f is just the unflowed correlator, the one that has been deeply studied in the literature. So you also know the last line. And if you remember, I was telling you that in order to find this nice form, we had to adopt kind of a Fourier-like transform. So if we want to express the result in the original variables, we have to Fourier transform back. And this is what the first line achieves. It gives the inverse Fourier transform, and it trades back the y variables for hi variables. So I hope I convinced you that correlators with winding are no longer unknown. They are under good control because correlators with 0 winding provide them for free. And there are many other things that I would like to tell you, but unfortunately there is not much time. So we are also working at analyzing the singularity structure of these correlators. And something very interesting emerges because you find singularities in the middle of the moduli space where you would not expect a singularity to be. And actually, if you zoom in close to these singularities, there the correlator is diverging. This means that the region close to the singularity dominates the integral that you have to perform to compute the string correlator. And if you regularize this divergence, you can compute explicitly the string correlator. And we find evidence of some contact with the dual CFT. And we find that the correlator we obtain looks like a correlator of the symmetric orbifold of some boson with background charge. And we would also turn all I said not just into a conjecture with many tests, but into a full proof that might be possible via some free field realization. And this is also the main building block to compute supersymmetric and extremer correlators. So this is all I wanted to say. I want to thank you all for the attention, and please ask me questions. I will be very happy to discuss some physics with you. Thank you very much.
Okay, thank you. So the session is open for questions. I see Agnese Bissi, please.
Hi. So
hello.
A quick question that maybe I didn't get exactly. So at some point you said that the main point that you have is the fact that the same differential equation that the unflowed, for the unflowed, you can get the result for the flowed. I mean, you had it a few slides.
Yes.
Yeah, anyway, I mean, it's not
here.
very important, the form. But if this is the case, this means that essentially, again, some symmetry should be there. I mean, there should be some way in which this translation acts on the flowed parameter in such a way that this gives rise to the same differential equation. Do you see that at the level of the algebra or not?
So we don't see them by first principle. So we can check this explicitly. So you can write in closed form this differential equation for the float correlator, inject the answer to the solution in terms of the unknown function f, and see what this reduces. So this is a hands-on approach. But by first principle, why it should be so, that we have no idea. I mean, it was surprising also for us. I mean, first of all, what is surprising is that if you analyze different examples with different w's, so you would expect that this gives different functions, different constraints. I mean, I have labeled this function just as f, but in principle should be f of w1, w2, w3, w4. And what is surprising is that it reduces to always the same differential.
Yeah. That was, since it's so general, it might be related. I was just wondering if it was related to some.
I agree it must, but we have no idea why. I wish I knew.
Okay, thanks a lot.
Okay. So I see Fabio and then Andrea Cappelli.
Yes, it's just a non-expert question. In your motivational slide, you mentioned the fact that the SL2R Vesely-Witten model is suspected to be completely solvable and that your work was going in that direction. So what do you expect to be the main difficulty in towards reaching the complete solution of the model?
Okay, so by complete solution of the model, I would like to know all fusion channels, all fusion rules, and all conformal blocks. And it's not completely clear at this stage how, and maybe in the end even proving crossing symmetry. That I would call a solution of the model. And this is still a work in progress, so we don't yet understand how conformal blocks of correlators with winding are described. So in principle, our proposal gives a recipe. It tells you, take the conformal block expansion of the unflowed correlator, insert in our integral formula, and this should provide conformal block expansion for the correlators with winding. But it would be nice also to understand how this works from first principle, not just via this formula. So we don't know what conformal blocks look like and how fusion looks like. We can say which 3-point functions vanish, but we don't understand yet conformal blocks, and crossing symmetry is still missing. So these, I think, are the main obstacles or the main punchline, if we are more optimistic.
Thank you. Now, very briefly, a question and a reply. So Andrea Cappelli, please.
Thank you.
Yes, usually when there is a surface wrapping several times, you have additional singularities which are represented by additional fields. So your result seems to rewrite the correlation function in the same number of fields, but in somehow different variables. So this is completely opposite to what is my intuition. Can you comment?
Sorry, you're saying that these variables are opposite to what?
I mean, when you have a multiple covering of a surface, you in general have additional fields, which are called twist fields, which show up in the correlator. So yes, somehow you would expect that the 4-point correlator on a branched surface would have additional fields for any of the branching, which is the multiple covering locally. Okay, so you would expect to express this 4-point function in terms of, I don't know, 6 or 8 fields. So, not the same number of, so that confuses me.
Yes, so the analog of the, so you can identify this winding with the branching indices of the, I mean, the covering map that controls the geometry of the problem. So I was telling you that this PW controls the geometry of the problem, and this, the is the polynomial that guarantees the existence of a covering map with branching indices Wi. So you should think to have, these are your branching indices that correspond to the spectral flow or winding amount. So if you want, in the easier setup where you have minimal tension, this winding in the bulk corresponds to twisted sector of the symmetric orbifold in the boundary. So the W winding will give the W twisted sector of the orbifold. Now for generic tension, it's not yet clear how this is related, but that's generally the picture you should have in mind. An assignment of spectral flow integers will correspond to an assignment of branching indices for the covering map.
Okay, so thank you. I think we should now close the session. I don't know if Stefania. So thanks to you and to all the speakers of this session.